I don't know if I have an exact number. Like I said, I think you will see, it will be very common to see more than 10% because this task structure, that architecture does seem to be better over here. So that's, I think there's a lot of things that are going for Sandy Bridge besides the 10% improvement. But this is to make sure that people are aware that brand new money. I think my job that was 1,024 ranks, I moved over here 1,024 ranks, 2x faster, great outcome. Make sure you do all the comparisons. This is per core module, and this is per node. So really, if you wanted to think the L1 bandwidth per node, you take this number and multiply by 16. Flops per clock, it's very similar. Per core module, it's 8, per core is 8, 128 per node, then you multiply out, 120 over here, 120 over here. Memory latency is a little bit better over here, and some codes will see that. That's another reason why codes will speed up on Sandy Bridge. And then the clock rate probably changed. I don't know what the clock rate is on Rosa. Anyone around that? Okay, so it's going from 2.1 gigahertz over here. So, again, if you're completely memory bandwidth bound, that clock rate's not going to help us much, but basically it helps everything else. I mean, the clock rate does help. A word about clock rate, which I don't think I explicitly call out to anywhere. Take all clock rates with a grain of salt. They are, that's only like a, when you, I don't know how you buy a car here in Switzerland so much, but you always haggle over a price when you buy a car in the United States. You can think that the processor is constantly haggling over a price. Sometimes they'll say that, no, this car is really valuable and it's going faster, sometimes not. The point is that the gigahertz is constantly jumping around on you actually underneath the covers. And you might want to try and control it, and we tried to think if we could control it one way or another, and really turns out that controlling it means playing around with BIOS settings, which is what we're trying to do. But as an application engineer, there's nothing you can do about it. And basically, you hope that your program runs at a gigahertz that is faster than what it actually is saying, and that is true. It is often, Sandy Bridge is often running at a gigahertz that's faster than 2.6 gigahertz. So there's some positives there. You don't just, like that one DJ I showed, you actually get higher than 100% the peak. Because while given the BIOS settings and everything on that machine, it was actually going faster than 2.6 gigahertz for a substantial amount of time. So, quite a bit of information on this slide, really. But I like these slides because you can see the two right next to each other. And maybe as you go and you take your application and move it over and take those numbers, and you get it per rank performance improvement, and then you do another couple more calculations to get it per node performance improvement, and then you begin to wonder, well, I got 1.4 or 1.5 per node. Why did I get that? And this might start providing some hints. The next guy got 1.2, and then another guy got 2.2. If you refer back to this, and you might be able to make some headway in determining why that is. Any questions about this slide before I move on? Okay, so we hinted at this, you can do one hyperthread or two hyperthreads per node. And we had to, again, sort of invent a new term. Hyperthread was proprietary, so we couldn't, you have to be careful about actually using hyperthreads in our documentation and stuff. And sort of the term thread is also overloaded. So I thought about it in terms of a single stream versus dual stream. And basically, the point is that unlike most Intel clusters for high-performance computing that I'm aware of, most other clusters run with hyperthreading off. We run with hyperthreading on. It's actually always on in terms of the OS. And then what really happens is the user can choose to run with one or two ranks, DEs, threads per core. And we call that, running with one, we call it single stream. Running with two, we call it dual stream. Like I said, this choice is made at one time. If you run in single stream mode, that's one rank per core. Just making this strict MTI only code, one rank per core. If you run with -J2, that's dual stream mode, or two ranks per core. The default is single stream. So if you don't say anything, it's single stream. I think that's why you decided to change it. I don't think you were deciding to change it. So default is single stream. So that's one rank per core, and that ends up with fewer ranks, 15 ranks per node, compared to Rosa. Right? Right now, we don't have any evidence that running with hyperthread always on is a bad thing, and we're going to see that there's some hope actually is a good thing because we can hopefully find uses for that other thread, even if we're not using it for our application directly. So now we're presented with a dilemma. But I think it's a good dilemma. What do I run? Do I run in dual stream or do I run in single stream? Now, one rule of thumb that we're trying to develop, and it's more than your mileage will vary, it's your attitude about the mileage, what mileage you get will vary. So dual stream is often better if throughput is more important. And this basically says, if you look at the aggregate throughput of the machine, some codes, if they use the same number of ranks, but have twice as many ranks per node, then they will actually use half the number of nodes in dual stream compared to single stream. If they fit in memory, if that all works, in a way they will get better utilization of the hardware, potentially, not necessarily together. Performance per node is more important. That's another way of saying throughput is more important. But it's completely plausible that if you say, I want to use, my time allocation over the next year means that I can always have a job that uses 100 nodes running. Now, how do I best utilize that node? Well, I might be more concerned about the performance per node as opposed to the performance per CPU or performance per MTI grade. And if you look at it that way, and you try it both ways, maybe dual stream ends up being better. Another thing that probably goes with dual stream is your code scales extremely well. It just kind of makes sense because if your code does scale extremely well, with dual stream, you've got twice as many ranks for a given amount of hardware. So you better be able to use them. If you being able to use them, means your application can scale. On the flip side, single stream may be better if single shot performance matters more. I want this thing done by 5 o'clock, so I have my answer, and I can think about it overnight before. Or even like I'm starting it tonight, and I want it done by the morning. You know, as a classic example, if the single shot performance matters more, you want to go as fast as possible. Maybe single stream is the way to do that, or even a number of frames. For core performance matters most. And another way of saying that is your code does not scale down. If you know your application scales to 1,000 cores, but it doesn't scale to 2,000 cores, and you're still waiting a long time for it to finish at 1,000 cores, well, really you want those cores to run as fast as possible. Single stream might be the way to do it. Now, the one example that I have, and the customer will remain in English, but we had a procurement where they defined an SSP metric, and this SSP metric was a function of the speed of certain applications given a fixed number of ranks, and then how much resources did you use, and then how many resources could they actually deliver for a certain amount of money. And when I started off, I had a little bet with a guy that he said, we tried hyper-threading with another bunch of systems, nothing seemed to work. I used a policy that you do more than one. He gave me one. He's like, more than one of the 7. I don't think more than one of the 7 will run using dual stream. And in the end, for the procurement, 4 of the 7 used dual stream mode. And that was optimized for the SSP. I mean, that's not gaming the system. That was, you set the rules, and this is what the rules tell you about how to run these codes. 4 of the 7. It was not done. It wasn't 6 of the 7 or anything like that. Pretty much as close as you can get. It was an odd number, right? So it was 4 of the 7. Some went one way, some went the other way. What their users actually do, I don't know, that's TDD. Many users, they jump on and use the default and run, right? So my guess is that most users will go with single stream mode, but it is a little tough. It refers to the same system performance. And that's just... You have less memory per rank, yes. Because you have a fixed amount of memory per node, and you're doubling the number of ranks per node, you have less memory per rank. The performance is the same per thread? No, I mean, so when you go to dual SSD, it's all the same hardware. You don't double the number of functional units, you don't double the number of bandwidth. So it would stand to reason that your ranks, in terms of per rank performance, would drop by a factor of 2, right? But it doesn't always, sometimes it drops by less than a factor of 2. In this case, the per node performance actually went up. You just try it yourself. I mean, the biggest piece of advice about this is that once you have an executable running on main, it's almost trivial. I can't think. And as long as you also fit in the memory, right? It's almost trivial to flip between J1 and J2. So just try it. Try it. Hit the numbers in front of you, and then make sure you kind of sit down and say, okay, how many nodes did I use for this problem? Make sure, and then decide, there's your fitness function. What are you trying to optimize for? Your time allocation, or I've got to do one Monday, whatever, right? And then decide which one you want to run. It might be a little bit of source of confusion, but I only can look at this as a positive because we're basically getting US choice instead of forcing you one way or another. We're getting US choice. Hopefully, after a few tests, you'll settle on one of those ways, or you'll like a Roberto and you'll learn when to run one way or another, and then it will become more natural. Any other questions? Core specialization. So core specialization has been around for a few years now, and basically the idea is to try and put all the system noise on a core which has been specialized to only one net. And this has become more and more viable as the number of cores on a node has increased. Core specialization was resistant when you only had one core per node, right? As you got to 2, it's still going to take half your resources. 4, it's a little bit less. Well, now we're up to 16 or 32, depending on how you count. And really, it dedicates one M number of cores or CPUs per node will be dedicated to system work. All of the system interrupts will go there, and in some cases, NCI work will go there. We'll see in a little bit. Conversely, the application will not run on the service CPUs. So the way to get that is use the applet -R option. You can do man run, you can read it for yourself. -R option to get core specialization. Normally on the XKey with 90 cores, and a lot of those people only get R1. But R1 is not your only choice. You can do R31. It would make much sense, but you can do it, right? You can reserve almost all the nodes for the system. And one thing that might make sense on the Sandy Bridge is all the numbers between 1 and 8. Why is that? Let me continue a little more. It starts at the highest number of CPUs and works backwards. The way the CPUs are numbered on Sandy Bridge is they're numbered 0 through 15, having one thread per physical core across the node. Then they wrap around and they go 15 through 31 for the hyperthreads across all those physical cores. So when we start off by saying -R1, it's going to use CPU number 31, which is the hyperthread associated with the last physical core on the last socket. If we say R2, it's going to be the hyperthread on the last 2 physical cores of the last socket. Now think about it. This is independent of the app-run J1 set. That means it will always start at the highest CPU number and work backwards, no matter what you have set for a J1 or J2. But think about that for a second. Okay, if I'm running J1, which is default, I'm only using CPU 0 through 15. And 16 through 31 are just there and available. And so if I do -R1 or 2 or 8, it's going to be using hyperthreads that my application wasn't using anyway. So it seems completely viable to, if you're in J1 mode, to try R1 or 2 or 3 or 4 and see if it helps you for some reason. So conversely, if you are running in dual stream mode and you say -R1 or R2, well, that hyperthread is now going to be removed from the pool of potential places where your application can run. And so if you do R2, right, that means I can only take 30 ranks per node. You're going to have to take that into account when you calculate how many nodes you ask for. So So, again, it might be a little bit confusing at first, since we have this opportunity to run J1 or J2, single stream or dual stream. But again, I think we're pretty convinced that this is the right way to go. We're just getting you new choices. So, core specialization was possible on Interlagos, and basically you can think of course Interlagos is always running J2. So Interlagos always use, the default way on Interlagos was to use 32 ranks per node. And if you use core specialization, if you use R1 or R2, for example, that would drop down to 30 ranks per node. So the same thing is true on Interlagos. It is available on Interlagos. It's just you have this new flip if you're running J1 mode. You don't actually take resources away from your application. We'll hit this a couple times yet. So I think there's an AT count that helps you compute the total number of cores required given that command. I think that's what that is. I haven't played with it much. I do it myself, but that's something to look at. So interesting that in 4 slides I'm going to come back to this. So now we're going to talk a little bit about software. You've seen various pictures of this before, actually already, not exactly the same. But the point of all of this is that on the left-hand side is the SE platform, and on the right-hand side is the Cascade platform. You see that both of the boxes span both sides. And that's just to say, for most things, Slurm's not on here. Slurm should be on here. But both things stand. Is Slurm available on the XE? Is Slurm available on XE? Do you use Slurm on Rosa? Okay. So, it should be on my site. You should chastise me. Make sure you tell my boss. But anyway, so the point is really that for most things, they're really available on both sides. Now, in all honesty, there are subtle differences that probably impact you a little bit. I think Clay was finding there's subtle differences that are impacting the user community a little bit more than we expected. One of the differences is that on the left-hand side, we had PGI GNU and Intel compiler. We also had the Cray compiler. On the right-hand side, we still have the Cray compiler. We still have GNU, and in a sense, we still had the Intel compiler. But really, the Intel compiler was new and not heavily utilized over here, and here it's default and heavily utilized. And PGI was over here, but not over there. So there's some porting. If you use PGI on Rosa, there's going to be a compiler porting effort as you decide, do you want to move to the Cray compiler, do you want to move to the Intel compiler, or even GNU. So that's one thing. Another thing is the Cray Math and Scientific Libraries. Currently, they are, we say they're available on both platforms, and that is true, but currently the Cray Math and Scientific Libraries is not available to link against Intel. And again, I think we talked about this yesterday. There was a lot of people that on Rosa, they just logged on. They needed the live side, even if it wasn't the most important performance thing. They needed it. They didn't have to think about it, and it just linked. And if you move over here with the Intel compiler, that's not quite as smooth a transition as we wanted. So some people are finding, well, I have to figure out a way to link against MKL, and that means going to that Intel website to get a link like this one, just to link MKL. So we'll see how that pans out. I think over the coming months as to whether or not we can make it smoother. But coming months is not next month. So and you guys are or this afternoon. You guys are working months. So keep that in mind. But for most of the rest, it has been a very smooth transition. And I've had slides that I showed over the last year. The way the Cray benchmarking works, we first got access to a Cascade system a little over a year ago, and we brought it up, and we had various blinks. And the way that we would port codes and get them ready for the Cascade system is we would get them running on an XE system with the compiler of choice that we wanted to use on the Cascade system. And then once the Cascade was actually available, you just have to move over the recompiler book, and the recompile should be simple because you already compiled over here. So there should be really almost no differences. And it almost always just ran. If you had a successful recompile, it almost always just ran. So that was a positive experience. So in a way, even access to data is going to be open pretty soon, but you're thinking about porting your code, you really should be able to get everything running on Rosa over here with the Intel compiler, even with the caveat about this live side thing. It's not a great library. So I'm not going to try to get you to throw the library. So, but a lot of the things are similar between the two sides. And in particular, MPI. Okay, MPI was practically speaking brought over wholesale, and MPI source was just recompiled for the Intel. And then we started trying to do enhancements. I mean, the bulk of MPI was just moved over. So in many ways, it became essentially the same MPI on the XE. If you ever wanted to read a man page and wanted to play with the environment variables, those environment variables are all there still and all mean the same thing. Their defaults are the same in terms of eager and rendezvous, which we'll talk about more this afternoon. And stuff like that. If you were into that stuff, it's going to be there again. The two enhancements that are noteworthy on the XE so far is one, the modified MPI asynchronous progress engine threads. Okay, this is a feature that is actually available on Rosa, but there's a twist that is worth noting on Cascade. What is it first? Threads can be placed on unused Intel hyperthread code. In general, the threads can be used on unused CPUs on the node. On Rosa, you actually have to carve out an unused CPU by doing core specialization. While on Cascade, they will automatically use the hyperthread cores if you're in J1 mode, if you're in single stream mode. Remember, single stream mode, you're only using half of the hyperthreads, so this was designed to automatically use the other half just by setting the environment variable. I have another slide on it in just a second. So this is going to be good. I can see the secret. What is this? You do ISEN and IREC, and then you have some amount of computation, and then wait call. The idea with that is often I want to make forward progress. I want the communication to happen while I'm doing computation. And people often, I've done everything necessary, but it turns out that the MPI software stack underneath is quite a bit more complex. And given that, lots of the timing of various things, it's not guaranteed that overlap will happen. You need something to be kind of actively monitoring the situation. That's called a progress engine. And this is exactly that. This is a place where to put that progress engine so it can actively look good for messages coming in or ready to move. So it basically helps with your overlapping communication and computation. And not all codes are set up to use overlapping communication and computation, and some codes, even if they were already set up to do it, they were already getting a benefit. So it's not guaranteed that this will help, but it's another tool in the toolbox. XC hardware collective engine is another thing. We have hardware support for barrier and some overuse collective. You can plan to use these using this environment variable, but you must also link against live DNAM. And DNAM is a particular low-level communication library. This is an interesting one. It's touted as being great. It does have fast barriers implemented in hardware. I will also attend as an application engineer. Most of the time, if I see barrier taking a long time, the first place I look is some kind of load imbalance, either in the code or even induced by something. There's lots of things that can induce load imbalance. Less noise, which we're constantly trying to minimize, or even just a neo socket versus R socket. So if you have barrier or overuse taking a long time, this might be something to try. But keep in mind that if you try this and you don't run faster, like this, think to yourself, okay, there's something about it for some reason. Hardly anyone tries to use it. Are you trying to use it? I don't know about specific tests, but given everything I said about things moving over wholesale, and the hardware is similar enough in those regards that I don't expect magic to happen. The hardware is faster in terms of lower latency and better bandwidth, but if there's something in either the hardware or software that magically accelerates the one-sided, I can't. This is to enhance those collectives, and I've already let the cat out of the bag that we're also putting in DNAP to improve the all-the-all performance. That's not quite available yet, but it's coming. But really, I would say if you want to do one-sided, I would seriously consider going whole hog and trying one of the CCAS languages, Core Wave 4 Trench, type of thing. And those rock this machine. They did pretty well on Gemini, but they're okay. Any other questions? No. Oh, this is for all the reduced collective? Yes, this accelerates the hardware. I should put that out. Yeah. The hardware acceleration is for a limited number, right? And I can't immediately remember if it's one double or two doubles. But it's not four doubles. I'm pretty sure on that one, right? So if you're doing the all reduce, you're all reducing the megabyte. You're not using the hardware acceleration. And that sort of makes sense. Hardware acceleration literally means you're doing the operations in the areas, and it has only memory for a couple of words. So yes, this is meant to this is meant to try to speed up barriers where you're basically passing around a 64-bit integer, and some of the floating point collectives where you're doing one or two words basically is acting like a barrier, but not much of that. I know people inside of Prey have played around with it, so I think this is the majority. No, nowhere near the majority uses. The default is not set the environment variable. No one uses not a minority of people use DNAP as part of their NPI today because the default is to not use it, and most people don't see a benefit from this. Either barriers are not a major component, or even they are major components. This doesn't help. It will be interesting to see how this changes when all starts using DNAP. The optimization that's coming is all is DNAP, and then that doesn't apply just to a single word all, that applies to any size all. So we'll see if it. I won't guarantee it will work on. I don't know that it'll turn into a majority or anything like that, but. One last word about linking in DNAP with your MPI, this is true on Rosa, is if you link in DNAP, you are kind of saying, I'm going to give up some MPI capabilities to get other capabilities. And then one MPI capability that I know you give up is multiple binary launch. Most people don't do multiple binary launch, so most people don't care about that. But an MPI purist would. They say, why can't you implement this? Anyway, so you can't, if you link in DNAP with your MPI, you can't do multiple binary launch anymore. So more about this async progress engine. This is the group communication overhead starts a helper thread, and then you have to say where is that helper thread going to run. That helper thread runs the progress MPI engine while the execution computes. This is only applicable to messages that use the rendezvous loop path. We'll talk about what that means this afternoon. It means it's got to be a substantial size. We're not talking single word. I think this is at least a couple kbytes or something like that. If it's smaller than a couple kbytes, it uses a different method, and overlap happens sort of anyway. So it only happens for some message sizes. To enable it, these are the environment variables that you set. When using one stream per core, you set this environment variable, you set red safety, and then you enable it, and then you can just run it without anything else on the line. Because remember, in single stream mode, the other hyperthreads are there anyway, and it's been designed to use those hyperthreads. When you're running with two streams per core, then you still have to set these environment variables. You don't set this unassigned CPU thing, but you do now have to do minus R. Again, you can do one or two. If you start doing more than two, these things are taking resources away from your application, so your probably not going to be more than two. And we have seen 10% improvements with some applications. Milk is one application that's a QCD application from that's used in the United States. I don't know if it's used in Europe as much, but QCD application, it runs best in single stream mode, and it we also tried it with this async thing. They got another 5% boost with this async thing. So my hyper-threading optimization chart down here, this is almost a high-level optimization chart. You're going to start in the upper left-hand box. Really, when you jump on the system, the default is single-stream mode, and there is no MPI basing. You're going to collect the performance baseline here, and single-stream mode, remember, this is kind of maximizing per CPU performance, maximizing per RAID performance, if you want to think that way. There's little to no MPI communication overlap. Little to no is really a fuzzy thing here because it really depends on your app as to whether or not you're always getting it. I'm not saying it doesn't happen. I'm saying it's kind of harder to have in this mode, right? But this is default. This is where you're going to start to run. One thing you might try next then, because it might be pretty easy to do, is just to try single stream mode with MPI async on. Again, you're trying to maximize single CPU performance, but you're hoping that turning it sync on will improve communication performance. Does overall performance improve? It's not a guarantee that it will improve. It's not a guarantee that it won't slow down. Turning on those environment variables does add overhead into the MPI library, and if your code was already running efficiently, already getting lucky and having overlap, where it didn't have couldn't take advantage of the overlap anyway, and then you added overhead, there's a chance it slows down. That's why it's not default. So basically, run it and see if it helps or see if it slows down. But it's a pretty easy thing to do. Now you can also move to the other dimension, and that's try dual stream mode without MPI async. This is without more specialization or anything like that. And we're basically trying to see, well, how does our compute behave? We're optimizing perhaps per node performance, like I said before, or maximizing performance by using things, TE, however you want to look at it. And then is it better? I stress better in quotes because you have to decide what better means in this case. Your kind of solution or conservation of my time allocation, whatever you want to say is better. You have to do that. And again, it's using twice as many